Hello and welcome to the next unit in the waves and sound unit, where we're going to look at vibrations and how they create waves, what waves are and what it means and so on. Okay, so vibrations to waves. Yeah, something here. All right, so vibrations and waves. So a wave is a mechanical wave. Sorry, is a transfer of a vibration energy through a material, and material is often referred to as a medium. So the medium of a water wave is the water itself, and so on. Sound waves, the medium is air. So these travel through air and other materials actually, but the most familiar. So let's add here. So you might have been swimming and heard sounds of an engine or a boat through the water. It goes through water, it goes through steel, it's all sorts of materials sound waves can travel through, and we'll learn more about what we mean by that. A pulse traveling, say like you whip a garden hose, try and get it unhooked from the rear tire of a car you're washing. That little pulse you make travel on a garden hose is a wave. It's like a short blast of a vibration. So it'd be like a part of a cycle or something. Earthquakes, all sorts of mechanical waves that we're talking about. So we're just not talking about electromagnetic waves. We're talking about mechanical waves. So waves are created by vibrations. Okay, so vibrations have a frequency, and so waves have a frequency. And so I'm trying to emphasize on this page something that's always true. And so the frequency of a wave always, once it's created, okay, it always is the same, or it never changes. Okay, so basically, it's just always going to be the same as the frequency of the vibration that created it. Okay. Other things can change. We'll see later on. The speed can change, the length can change, the size of it can change, all sorts of things can change. But the frequency isn't one of those things. Right? It'll seem like there's a contrast or a contradiction to that later on in the sound unit, but we will be very clear about that situation. It's not a contradiction actually. It just sort of sounds like it. Yeah. So the two kinds of waves we're talking about. Look at demonstration here. So, all right, here's a quick video of types of waves. So in this one, the vibration is going to be side to side, and the vibration going side to side, and you're going to see the wave. So my hand, I said there, my hand is the vibration going back and forth sideways, and then the wave is going to go down the spring, and so they're at 90 degrees to one another. The transfer of that energy through the system. So the vibration is perpendicular to the direction of the wave. The direction of the wave is down the spring. Okay, so you can see this is what we're going to call a transverse wave. And so if I were to pause there, you can see the wave pattern that like travels along the spring. And so we could identify maybe from like there to there would be a wavelength, right? And then it repeats. So it has like a bump and another bump and so on, a bunch of bumps. A little hard to do in real life because it all just gets messy and it's so fast. But on a nice freeze frame like that, it's very easy to picture the wavelength, picture the amount of time it took my hand to go there and back, right? So that'd be the time for that. That'd be the period of that cycle of that vibration, and so on. Well, pulses going on, I can send just a single pulse. We'll study that one more later. But think of a section like that, and I'll probably freeze frame and draw, wavelength. I already did, but actually, I could do the freeze frame too. It's a good idea. So, just back top. I liked what I had better before, but let me just get a little screen capture of that while I can. I'll use that in a little bit. Pulses going on, I can send just a single pulse. We'll study that one more later. But think of a section like that, and I'll probably freeze frame and draw, wavelength. Video. The other type would be longitudinal, and I can show it in this one. And so let me come back to longitudinal afterwards. So here we go. So what we're talking about is transverse waves, and so a vibration material is at 90 degrees to the direction of travel of the wave. So you saw it in the video. The vibrations were sort of left and right, let's call it, and then the wave travels down the spring lengthwise. And so this is a picture or drawing from above. So that red would be one cycle. The red section here would be one cycle. Right, corresponds literally to one cycle of the vibration. It's one cycle of the wave. It's really, it's what it is. The length we measure in centimeters or meters really in the SI units is the wavelength, and the wavelength symbol is this weird upside down twisted Y. It's actually a Greek letter lambda. Okay, so that's that letter there. That's your wavelength. And then the time it took, measured with a stopwatch, of course, in seconds, is the period. Okay, so the time it took for the vibration to happen is your period. The vibrations at a certain frequency in hertz. It's all kind of familiar stuff based on what we've talked about recently. The rest position of the spring in the video is very obvious, and then I made it deflect one way or the other. So that's your rest position of the medium. And yeah, so that's just the wavelength is the length of the repeating pattern. The repeating pattern itself is, of course, the cycle. Okay, so the repeating wave pattern. Repeating wave pattern is the cycle. Oops. Let me just change that to be red to match the picture and so on. All right, so that's transverse. I might paste in that picture that I took. And so on here, we could measure out a cycle. And so start from there and go like that. And that's a cycle. And then the physical length of it, right, would be the wavelength. And the amount of time it took to go from here to here. It's a little hard to do time as a picture. That's why I put the picture of the stopwatch in, but the time from there to there is the period in seconds. And then the wavelength, of course, was in meters. Okay, so just to try and relate to the demonstration video that I put in there. On to longitudinal waves. So I'll go back to the video. Here we go. The spring, longitudinal vibration is going to be this way. The vibration is going to be through the spring. And so you see like a little pulse where the springs compress together and spread apart. As they go down the spring, it might be easier. Longitudinal with this spring, they're farther apart. So again, I'm going to vibrate this way, and the wave is going to go through. So you can see the compression and what they call rarefaction. So the spring rings compress, which is compression, and they also spread apart after that, and that's a rarefaction, they call it. I can go transverse this one. Transverse waves and longitudinal waves on a spring. So that's a nice physical, very tangible thing to be able to look at. And then we relate to that all the different types of waves that aren't as easy to picture, like sound waves and electromagnetic waves and so on later on. Okay? So there's the spring, expertly drawn. And there's the vibration. The amplitude of the vibration, you could look at the vibration direction. It would have a certain frequency and in hertz. And this is what type of wave a sound wave is. And we'll see, why and evidence of that later on. But this would have maybe a certain number of hertz. The frequency would be a certain number of hertz. All of the things we know about vibrations. And then so we have this, wave that's traveling down. If we went from an area of compression to compression, that would be a nice repeated, once you get back to the same part of the pattern, you've gone through a cycle. So I guess I could do this as well, where I could show the cycle of this thing. It's definitely not as obvious though, but that would be a cycle of the wave. And so that's an area of compression, another area of compression, of course, an area where they spread apart I mentioned is called a rarefaction. So definitely a word you want to jot down because you've probably never heard it before. And of course, the direction of the wave zipping down the spring. Sometimes you'll see it drawn like this, where you just have little lines shown to show where there's compressions and rarefactions of whatever the material is. So this could be a speaker, in which case, a speaker compresses and spreads apart sound air molecules, right? Which is what sound is. Right? So should start to give you a little bit of a visual and an understanding of what sound waves are and so on. Just a Google image of the same thing. We've got a longitudinal compression wave going down versus a transverse side to side. So with waves like light, we have pulse of light coming in. Now, I'm not talking about the type it is right now, but basically this is just when it tries to go through a material. So we get an interaction with an electron there, and then the energy gets transferred through and gets kicked to the next particle in the material. And so think about, that's going to explain why light slows down as it goes through materials. The actual type, if you remember Snell's law from grade 10 in the light unit, if not, you'll see it again later in science and physics if you go on in the discipline. So the type of wave we're talking about, this is a really nice little demo that used to work. Unfortunately, University of Colorado had this really cool site, and you could take the positive charge or the electric charge, and you could drag it. So if I drag this positive up, then eventually the negative would go up as well because they're attracted to each other, right? You drag it down, this one will go down because they're attracted to each other. And so if I drag this one down and let go, it would spring back and forth. As a result, this one is spring back and forth. And it gives you a good feel for what an electromagnetic wave is, right? This one going back and forth, causing this one to go back and forth. It's a fluctuation in that electromagnetic field, and it's all based on the attractions and repulsions between the particles, the charges. And so that turns out actually sets up two versions of the wave. You end up with an electric and a magnetic wave when charges are moving. So that's why it's the electromagnetic field. And we'll learn again more about that later on. Okay. We'll come back to that picture when we look at the electromagnetism unit and look at how magnetic forces arise from electric currents and so on. And start to really understand lots of things like how electric motors work and so on. Lots of really neat stuff. Weird little tidbit fact about transverse and longitudinal waves that a sand scorpion uses both to kind of hunt its prey, and it like triangulates based on when one wave arrives and the other wave arrives because they travel at different speeds, and kind of neat. That's one of those little weird did you know kind of things. Nothing, no major focus on that, but it was just a tidbit fact for you. It's kind of weird. Damping is something to know about too. Remember the pendulum that I had in the air would slow down eventually, in the water it slowed down quicker. So what the big difference in that case is what we call damping. It has nothing to do with the frequency, nothing to do with the fundamental properties. It's just how fast the energy dissipates due to friction and energy losses. So we look at that idea just to acknowledge in reality it happens. Okay, so period, frequency, velocity, wavelength, and so on don't experience any kind of damping. Damping doesn't have to do with any of those, just amplitude. Okay, so basically, if you set a vibration going and the waves going along and it's dissipating and getting less and less amplitude, like picture this picture here. And if it was a really long spring, eventually the wave would fizzle out to nothing, right? What we're saying is, as it fizzles out to nothing, the period and the frequency and the velocity and the wavelength and none of those fizzle out. Okay, none of those change because of damping. Only the amplitude does. Question is that a surprise? Right. So if you have this wave and it's going along really far, it's just going to get smaller and smaller amplitude wise, height wise, but the length of it, the frequency of it, all that stuff stays the same. So particularly the frequency, I'm hoping you're recognizing this page as an important way to answer it, right? Of course, the damping is not going to change the frequency because the frequency is the same as the frequency of the vibration that created it, right? The frequency of the wave is always going to be the same as the frequency of the wave that created, or the vibration that created it. Pardon my speaking here. It's been a long day. All right, so these are the questions that are to do with that material. Give them a whirl. Let me know if you have any questions. Post questions to the post help thing. And yeah. Oh, I guess I could answer the why is the sky blue thing now. So some people had it right for sure in the questions. Be careful not to use pseudoscience explanations. So if someone says, well, what do you mean by that? And you don't have an answer, it's pseudoscience. Okay, so this is the atmosphere. I'm going to draw it blue. Some people said that the blue light lingers. A lot of people said that. And so my question was, what does that mean? And of course, there's really no answer, right? But there were a few people that had it right for sure. You had, say, just white light coming through, right, from the sun, coming along in a big stream like this. Let's get my direction good here. So we have white light coming along like this, big stream of white light coming, would just sail through if there wasn't something in the way. What happens is, because of the types of molecules that are in the atmosphere, so these little particles that are in here on Earth, they absorb a very specific energy level of light. And so you might remember from grade 10 science, the light unit, and how light is really just energy that's absorbed by electrons of atoms and then released as it gives that energy back. Well, these absorb blue very, very efficiently, more efficiently than any other colors, and then it kicks them out sideways. And so all of these particles absorb and then re-emit. It's called Rayleigh scattering. And so they're just basically glowing blue because they absorb the blue light and emit it back out. And so instead of the light sailing on through, it gets kicked sideways. And so, a person on here, green person apparently, looking up would see blue light coming from the sky. If it wasn't for that, the sky would be black and the stars would be showing all day long. It just gets drowned out by all the bright blue light that's coming from the atmosphere. Kind of neat. If you look at this and you had your red, orange, yellow, green, blue, violet, if we filter out a ton of the blue, scatter out a ton of the blue, then it shifts everything towards the red end of the spectrum. And that explains why someone maybe here, let's say, someone here looking this way is going to see red, right? That's a sunset because the blue has been filtered out effectively by all of that scattering. And so it's very possible that on another planet somewhere might be different particles in the atmosphere. And if there's life forms on that, they'd be like, oh, it's such a pretty purple sky or pink sky or whatever. Unlikely pink because it's not one of the main colors, but could be mixture of colors, I guess. All right, so that's the answer to why the sky is blue. One of those neat life questions. Another really common guess, and it came up in a few of the explanations, was that it's like a reflection of the ocean, because the ocean's blue. It's kind of the opposite, though, right? The ocean, to some extent, is lakes, and oceans are sometimes blue, or they're blue somewhat, at least, due to the opposite, the reflection of the sky instead. Oceans themselves, lakes themselves, can have their own color for the exact same reason, though. And so if you have a lake that's particularly turquoise color or green color, it's for the very similar reason. Like light entering the lake or the ocean or the stream or whatever is scattering a particular color sideways, right? But otherwise, you might see a reflection of the blue sky and it would look blue. Yeah. So hope you find that interesting. It's physics of the world around you, right? So that's it for today. If you're doing well, let me know if you need any help.